This problem is titled Walking Robot. In this problem, we have a robot which is designed to navigate a two-dimensional 4x4 matrix by only moving forward or turning right when blocked by a wall of the matrix. The robot is located at the top left corner in the beginning, which is denoted by comma 0, like row is 0, column is 0. And the robot's final destination is the bottom right corner. We want to find full path of the robot before it hits the final destination or starts repeating the path. So either it can go towards the final destination or it can go to the same place that it has already visited. So the walls of the matrix are either one of the four borders of the map or any block within, and blocks are denoted by having a 1 in the cell, and empty cells are represented by having a 0. So let's look at this problem on the whiteboard. So we have a 4x4 matrix, which is our map. So the robot is initially here, right? And the destination for the robot is this place, the bottom right corner. And we have, let's represent it like this. This is our robot, right? The robot is here and this is our destination. And all of these cells can be either 0 or 1. So there might be empty cells where we can go in and out. And there are walls which are represented by 1s where we can't go into. And what we want to do is, the robot is designed in such a way that it will keep on moving forward, or if it is blocked by a wall, it will take a right turn. So in this case, the robot is going right. It looks at it, there is a wall, so it makes a right turn. So it was going in this direction, but since there is a wall, so it takes a right turn and then goes to this cell. Now from this cell, it can continue going, right? It comes to this cell. And then let's say this is 0, this is 0, this is 0. So it can continue coming here. When it comes here at this cell, there is a wall. So it takes a right turn, it moves here. But there is also a wall. So it takes a right turn. There is it can't go here because it's already been here, right? So it will just return this path from the left top corner to this corner. Why? Because it's already going into a place where it has already been before. So I hope the problem is clear. Let's see how we can solve this. Let's look at the solution for this problem called walking robot. So as we have seen the problem, let me actually add some more examples here to make it even more clear. So why do we have to stop here when we were at this position? We actually stopped and we returned the answer, right? Let's continue doing this. So we started from this place, we come to this place, and this place, and then we say that we take right turns and then we start going up, right? And then what happens? The robot again goes up and then it will take a right turn, it will see there is a wall, and then it will take a right turn, go to the down neighbor, and then it will continue going. Again, it will take right turns and go here. So in effect, the robot will be stuck here. It will keep on moving in this first column of the place, right? Let's see what happens when there is a 1 here. Let's put a 1 here and let's see what happens. So we again start from the top left corner. We go right, we see a wall. We take a right turn, right? And then robot goes here and then it continues going down. And then again, once it is here, it sees that there is a wall. So it takes a right turn, it moves in this direction. There is nothing here, you will go out of the maze, so it takes a right turn. Again, we are going into the place which we have already seen. So we return these 3, right? Again, it will continue going through these 3 places. So let's see how we can solve this. So few hints. So what we are trying to do here is all of these cells can be thought of as nodes. We are given the starting node, the starting place where we need to start from, and then we are also given the destination place, right, which is the bottom right corner. We have walls, we have some empty spaces, and the most important thing is whenever we can't like move in the direction that we want to move, then we take a right turn. And if we can't move in that direction, again we take a right turn. So at max, if the robot is at this position, right, let's say if it wants to go to the right, there is some wall, so it takes a right turn. There is a wall here as well, so it takes a right turn. There is a wall on the left side as well, so it takes a right turn, and there is a wall on this side as well. So if there are walls on all sides, let's say this is the scenario, there's no way like we should actually again take a right turn and then try, because if we have taken all the 4 turns and we see we can't make any progress, then we are going to repeat the same thing and again, right? So if we have looked at all the 4 places, we have taken like 4 right turns and we see there is no way to progress, there is no place where we can go, so we can stop this, right? So we'll see like how this idea translates into code, but it's very similar to generating the neighboring places, and then you see whether we can go to the neighboring place or not. If we can go, then we start searching from that place. So as we said, like it's very similar to like doing a DFS with some modifications. So let's say we start our DFS, right? But before that, there are few things that we need to consider, which is what is the state of our robot. There are like 4 different states. Either we can be moving right or down or left or up. So let's define all of these 4 things as 1, 2, 3, 4. So 1 is when we are going to the right, 2 is continue going down, 3 is continue going left, and then 4 is continue going up. And these are the 4 directions that the robot will be like positioned at, right? And if you think about this, when the robot is going right, what will happen? Let's look at here. So when it is going right, let's say from here to here, the row will remain the same, the column will increase, right? When it is going down, the row is going to increase, the column remains same, and so on and so forth for all the 4 directions. So we can code this up here. So when it is going to the right, what is going to happen? We are going to increment the column, which is represented by 0, 1. No change in row, but column increases by 1. Similarly, when we are going down, we are going to increase the row and column will remain same. Then when we are going left, we are keeping our row same, but the column goes down by 1. And when we are going up, the row will go down and the column will remain same, right? These are the 4 situations we might be in. And then there are some transitions, right? And how does these transitions look like? So if you look at this diagram again, so when you are going right, and let's say you find a obstacle on the right, then you take a right turn. So from going from right to now you are going down. Let's say you are going down and you see there is a obstacle, then you take a right turn and now you are going into the left direction. And if there is like obstacle on the left side, then you take a right turn, you start going up. And this transition can be coded in this way. Like let's say if you are facing right, but you have to take a turn. So when you take a right turn, you start going down, right? And if you were going down and if you have to take a right turn, then you start going left, which is represented by 3. And then if you are going left and you have to take a right turn, then you start going up, which is represented by 4. And the last one is when you are going up and you have to take a right turn, then you start going to the right, which is represented by 1. These are all the transitions. So with these 2 information, we can code up our solution, which will be very similar to a DFS. So let's call DFS from 0, 0 because the starting position of the robot is 0, 0, the top left corner, and we are going right. The robot starts going right in the beginning. So these three things actually define the state of the robot, where the robot is located on the map and which direction it is moving to. And then we can take both state information and also the transitions. We have to give the path that we traverse. So let's take a path as a list and pass this variable to our DFS function. And at the end, we need to return the path. And we'll construct this path when we are traversing, when we are doing our DFS. So let's code up our DFS part as well. So in DFS, we have current row and column where the robot is located on the map, and also the current state of the robot, whether it is moving right, left, up or down. We call this current direction. And then we have state, transition and path, which we can copy and paste here. So given all of these information, the first thing that we do in DFS is we mark this place as visited. So in this map, like all the positions are 0 or 1, like either they are empty or blocked. So we'll represent the visited cells by 2. So what we do initially is, of course, we need to also take the map as one of the parameters here. So we mark our current location, which is the current row and column, as visited, and we can mark it as 2. So if it is marked 2, it means it is visited. And then what do? We generate all the neighboring states. So at max we can like take 4 turns, as we discussed earlier. If we take 4 turns and still cannot go to our neighbor cell, then we have to return. So this is what we are doing in this for loop. What do we do when we are at a particular row and column? We try to go to the neighboring state based on our state, current direction. In the state dictionary, if we take current direction, then it will tell us what direction to move into, right? Let's call this direction. And we can generate the new row and column of our new neighbor, which will be the older row plus the direction 0, and then column plus direction element 1. Suppose the robot is moving to the right, so it will tell us we have to increase the column, but the row will remain same, right? So that's what we are doing. So we add this direction 0th element, which keeps the row at the same place. The new row will be the same one. And then we add 1 to the column. So the new column will be increased by 1. And now we check if the new row and new column is within map or not. So we are given a map of size 4 by 4. So we check if new row and new column are within the bounds of our map. If we are within the map, we also need to check if we have already visited this place, right? So if we have already visited this place, which we can check by checking the value at the new row and column. So if the new place has been visited before, then we just return true. So we just return, we don't do anything. We know we are done, right? Because if the robot goes to the same place it has been before, then we stop, we return. The second thing is, let's say the new place is within our map and it has not been visited. It can be an empty cell or it can be a wall. So let's say the new place is an empty cell. So what do we do in that case? So yes, so if the new cell is 0, meaning the new cell is not any wall, we can actually move in there. So we do a DFS from there. So we do a DFS from our new position, which is new row, new column, and state, current direction, and then we take all the parameters from here. We can move this a little bit on this side. So this is what we do. If it returns true, then we return true, otherwise we keep on exploring our map. And in all other scenarios, meaning let's say if the neighboring place is outside, then what do? We need to like take a turn and then try seeing that we can go to the next place. So for that we do this. So the new current direction would be, we take the transitions map, and for this current direction it will give us which way to move now. So for example, let's say current direction was moving right. So when we look at the transition for right, it will now point to down. So this will be pointing to the down direction. That's it. Like now it will try the new current direction, which is like it will see if it can go down, and then it will do the same thing that we have done. So it will see if the new place is within the map, and if it is already visited, then return true, and if it is not visited, then it will start a DFS from there. And if none of these conditions are true, then we again have to take a turn and then try going into that direction. And if everything fails, we try all 4 possibilities, we can't make any progress, then we return true, right? We can't do anything, we just have to return from there. Or you can say we have to stop trying. That's it. So I think this should work. There is also one case which we are missing here. So when we go to our new place, like this new place, and it could be that this is the final position. So we can do something like this. So if the position that we have is the bottom right place, right, meaning the row and column are 3,3, then also we are done. We have to return. And we also have this path variable where we want to add the path where we are in. So what we should do is, as we traverse, we also need to add the current row and column into this, right? Because when we start from, let's say, a particular place, we add that to our path, and then we generate the new neighboring place to go into. And if we find we can go there, then again that will be added to our path, and so on and so forth. There is one last change, which is when we actually come here and we see that the new place, the new row and new column is the final state, then we have to add this into our list as well. So we add this column, row and column, and that's it. I think it should work. Let's run this. Okay, so we have a problem on line 10. Okay, yeah, we have to like just append new column, new row in one as one element of a tuple. Let's run this. Awesome. So it's working. And just to like give a final summary of the solutions, the most important thing is states and transitions, which we have explained on the drawing board, where like state tells you like which direction the robot is looking at. If it is looking at right direction, then you have to like take a step on the right, and how that translates into moving to a new position. And then transitions tells you if you are at a place and you have to take a right turn, then which way you will be looking at. So if you are going in right direction, if you take a right turn, then you are looking at the down position, and so on and so forth. And then we do then we run our DFS algorithm, where the most important thing is these three things. The first three things, like where the robot is and which direction the robot is looking at. And then we mark this as visited, the current location. We add that into our path, and then we can only run 4 times at max. That's why we have a for loop for 4. And then every time we create the new row and new column, the neighboring row and new neighboring column, based on the direction the robot is looking at. And then we check if it is inside the map and we can go there, then we go there, start a DFS from there. Otherwise, if it is already the last or the final destination, we return. Or if it is already a place which is already visited, then also we return true. If none of these things are true, then we have to take a right turn and then try the same thing again. And if none of these things work, we take 4 turns, then we have to end. We can't go anywhere, so we return true. Thanks for watching, and we hope everyone enjoyed the video. Check out Interview Query for more algorithmic questions, and if you'd like professional coaching from me, link in the description. Please don't forget to comment, hit like, and subscribe to the channel.